I hope you all can hear me clearly and see my screen. And there are no voice issues. So as needed, we are going to take up fluid mechanics today. We'll do a brief revision. Thank you, Jonathan. A very good morning to all of you. Let's start with the work straight away. So, fluid mechanics. Fluid mechanics is basically divided into two components: statics, that is, when the fluid is at rest, fluid is not moving, and dynamics, when the fluid is moving. So, we get these two classified cases in fluid mechanics problem. So, whenever you get the fluid mechanics problem in your exam, the first thing that you have to ascertain whether the fluid is moving or not. If it is not moving, it falls in the category of statics. If it's moving, then it falls in the category of dynamics. In statics, the two laws that we study are Archimedes' principle and Pascal's law. You are familiar with them. Let us quickly revise them today. For dynamics, we look at equation of continuity, and we also look at Bernoulli's principle or Bernoulli's equation. So these are the four principles. If you study them in depth, they are more than adequate to solve most of the fluid mechanics problems. At the end, we will look briefly at viscosity and turbulence, which is not very challenging. So, yeah, I open my chapter with a question that fish's flesh density is higher than water, and therefore they should get drowned in the water and completely go down, should not be able to come up. Still, they can keep themselves afloat in water. So, the question is how, and we'll come to answer this question towards the end. I'll just quickly go through the basic concepts. Many of them could be a bit too fundamental, but as I said, this is a PPT which I have taken from my FYBSc course and modified it further for TY. So do hold on. Density is mass upon volume. Unit we are familiar. kg per meter cube. Density gives an idea that how much matter is present in the given space. So in the given space, if the matter is more, then we say that density is high. If the matter is less, we say density is less. In case of fluids, the density can density may remain constant or density may even vary. Depending upon whether the density is constant or density is varying, the the fluid would be classified as compressible or incompressible fluid. In a compressible fluid, the density can change because fluid can be compressed, more mass can be accommodated into a smaller volume. For a non-compressible fluid, density remains constant. 1 kg per meter cube is 1000 gram per meter cube, which is 10 power minus 3 gram per centimeter cube. This is one of those rare units when you convert from SI to CGS, the conversion factor reduces. Generally, not as a rule, but generally, when you go from MKS to CGS, the conversion factor is more than 1. So, for example, 1 Newton is 10 power 5 dyne, or 1 joule is 10 power 7 erg, but 1 kilogram per meter cube is 0.001 gram per centimeter cube. Do remember this. Also, do remember that 1 meter cube has around 1000 liters. So 1 liter is 10 power minus 3 meter cube. Densities vary in the our world. Air can have a density of around 1.2 kg per meter cube. Just imagine how big could be a meter cube. And then if it is just filled with air, then its mass will be 1.2 kg, something like that. If you fill it with water, the mass will be 1000 kg. If you fill it with mercury, then mass will be 13,000.6 kg. And this is what gives us a specific gravity, which is the uh, density of the material divided by density of water. It's a pure number without any units. For example, aluminum specific gravity is 2.7. You can see from the data sheet which I had just presented. Aluminum has a density of 2.7 into 10 power 3. Water has a density of 1 into 10 power 3. So you divide 2.7 into 10 power 3 by 1 into 10 power 3. 10 power 3 cancels, giving you the specific gravity as 2.7. So specific gravity is just a number, and it's a misleading number because there is nothing specific about it, neither it has to do anything with gravity. So be careful. Pressure in a fluid. Pressure at any point in a fluid is defined as the normal force per unit area at that point. So if you have take any point and if you want to find out the force, you first find the if you want to define the pressure, you first find the direction of the force, find the area which is normal to the force at that point, and then you calculate dF by dA. It does not matter which way you orient your area at the same point. The pressure remains same. It is independent of direction. In all direction, pressure will be same at this point. If you double the area, the force will get doubled so that the pressure remains the same. Typically, the pressure definition is P is dF perpendicular by dA. I'm writing perpendicular here just to specify it clearly that it is normal area. Force is normal to the area. 1 Pascal is 1 Newton per meter square. In science circle, there is a bit hilarious joke about 1 Pascal. So if you don't know it, remind me to tell you in the subsequent discussion. We know that the 1 atmospheric pressure works everywhere, which is 1.013 into 10 power 5 Pascal. And if pressure is constant everywhere, then I can drop this D, which is a variation in pressure, and I can simply write as F by A. What happens in a fluid? So if the fluid has a uniform density, there are no density fluctuations, and fluid is incompressible. That is, you don't compress, it doesn't get compressed by its own weight or mass. For example, if you take the fluid in the beaker, if it's a compressible fluid, then you can see that any point at the lower section will have more pressure from the top, and it will get compressed. As a result, as you go from top to bottom, density will go on increasing. So that's how a compressible fluid behaves. We say that I'm talking about a uniform density, so it's an incompressible fluid. So if you take an incompressible fluid, take any 2 points, one on the surface, one at the bottom, somewhere here, then this will be exposed only to the atmospheric pressure, while this will be exposed not just to the atmospheric pressure but also the pressure of the liquid column. So if this coordinate is y2 and this is y1, then the pressure at this point, the extra pressure at this point, remember, will be h rho g, or h will be y2 minus y1 into rho into g. So that is the extra pressure. Remember, I'm writing the way I'm writing P2 minus P1, a negative sign will appear over here. The total pressure at this point is going to be the height of the liquid column, the liquid pressure plus the atmospheric pressure. So the total pressure is P0 plus H rho G, or H rho GH. Remember, in a fluid, pressure gradient will exist. So if you are at this point, pressure will be less. As you go down, the pressure will go on increasing. If you take a derivative of this, you will get the pressure gradient. The pressure gradient is minus rho g. So do remember, many problems, this fact is very important. Pressure in a fluid can is same at the bottom. It just depends on the height. So it does not matter if you have same fluid in different shapes, sizes, at angles. At the bottom, fluid pressure is same everywhere, and therefore, since it depends on the height has to be same in all cases. So it will go up to the same height. If you want to simplify this visualization, take this case. This is a slanting line. You can imagine it to be divided into vertical and horizontal, vertical, horizontal steps. Horizontal steps, they don't contribute to any pressure difference. Vertical steps all are going to add up and will give you the straight height from here to here. So the pressure is same in all the cases, and it is equal to H rho g. And that gives us what is called Pascal's law. So if you apply the pressure to an enclosed fluid, then that excess pressure which is applied is transmitted undiminished to every portion of the fluid and the walls of the containing vessel. So if you have a fluid closed in a vessel, apply some extra pressure on one side. That extra pressure is transmitted throughout the fluid. And this can be used to amplify forces, as we all know. So at 2 points, the wall surface area is A1 and A2 and forces are F1 and F2. What Pascal's law says that if the fluid is static, the pressure has to be same. So F2, P is equal to F1 by A1 is equal to F2 by A2. F2 will become equal to A2 by A1 into F1. So if A2 is larger than A1, then F2 will be larger than F1. And one of the classic example is a hydraulic jack. An hydraulic jack works on this principle that you apply a small force on a small area, and a large force is generated on a large area here. So it uses this principle: if A2 is much larger than A1, then F2 is much larger than F1. So this kind of thing is called hydraulic jack, but this is just one example. All the cars use the normal braking in the car, which you apply by your foot, is disc brake. They are disc brakes, and they work on this principle. You apply a small pressure on the paddle by your foot, and they apply a large pressure on the disc brakes to stop the car. Imagine a you cannot imagine a high moving car, high speed moving car. It's very difficult to stop it, you know. But your few centimeter movement of the brake paddle completely stops the car. So that beauty comes from this Pascal's law principle. You apply a small pressure here and you get a large force here. This is for incompressible fluid too. Yes, yes, Vinod. Sir, is Pascal's law only true for the force at 2 points in the same No, not necessarily. Vinod, if you remember, car brakes are not at the same horizontal. Um, or even uh, I mean you can argue car brakes to be at the same horizontal level because the brake paddle is at the foot, but when the brakes are applied in when the brakes are applied in disc brakes are applied in motorcycles, then most of the disc brakes controls are the hand brakes, which are much above the actual disc which is placed at the wheels. So it does not matter. Pascal's law height doesn't matter. So uh, even if the fluid is in a tube which varies in height from top to bottom, you apply some extra pressure at the top, that extra pressure will be transmitted all throughout the fluid. Yeah, pressure will, the gradient will be there. Gradient, we can discuss this after the class. The gradient will be there. Extra, whatever extra force you are applying or extra pressure you are applying, that is added to all the points. You will encounter this term absolute pressure and gauge pressure. So excess pressure above atmospheric pressure is called gauge pressure, and the total pressure is called absolute pressure. So please don't get confused. You may get these terms interchangeably in problems. So if it is given absolute pressure, remember you have to subtract the atmospheric pressure to get the gauge pressure or the pressure of the fluid. So this whole term is nothing but an absolute pressure. Two devices that physicists always rely on are open tube manometer. There are two open tubes. If you want to measure the pressure of something, then you have to attach it to the one tube. You find the height difference which will appear because of the pressure difference, and from the height difference you can figure out what is the pressure of this particular arrangement with respect to the atmosphere. One of the simplest thing that you can do at home is to just take a long pipe, rubber tube you must be having, fill it with water at least half, and then turn it into a U shape and start blowing from one end. If you blow it from one end, the level will go down, other side level will go up. Ask someone to measure that height difference and from that difference you can figure out how much pressure your lungs can apply by the way of blowing out. Beautiful fun experiment to do at home. The other one is the mercury barometer. You are all familiar with this. You have used it in our lab. Mercury tube dipped in the mercury beaker. It comes down. You know that atmospheric pressure, this height is around 75 or 76 centimeter of mercury. You get almost near pure vacuum here. Experiment was first done by Torricelli, and that's why we call the units of vacuum as, vacuum pressure, they are defined in the units of torr. So 1 millimeter of mercury, which is a very less pressure, is called 1 torr. So remember this. This is a commercial pressure gauge which is available in petrol pumps and other places. If the air comes in, it's going to push this flexible pressure tube, and that will push the pointer on the dial. So these kind of things are available. This is called a Borden pressure gauge. Then we come to buoyancy. Archimedes principle, again you are familiar. When the body is completely or partially immersed in a fluid, the fluid exerts an upward force on the body equal to the weight of the fluid displaced by the body. So basically everything can be explained in these two simple diagrams. So let me start with the left one. I have some fluid in the beaker. It's all fluid. Now you just imagine some block or some section of the fluid surrounded by a boundary. It's imaginary, it's just imagination. We are not separating the fluid. Now, once you imagine this, then the fluid get divided into two sections. One is this inside the boundary and one is outside the boundary. Now the fluid which is outside the boundary is going to apply pressure and hence the force on the fluid which is inside the boundary. Now this pressure is going to be less on the upper section and pressure is going to be more on the lower section, because we have just discussed as you go down in the fluid the pressure increases. So the upward pressure will be more and downward pressure will be less. As a result, if I calculate the force on the inside section, then the force in the upward part, which is net downward, will be less, and force in the lower section, which is net upward, is more. As a result, there is a total net force which acts in the upward direction. So the net force on the fluid due to net force on this section due to the external fluid pressure works in the upward direction. mg, the weight of the fluid, works in the downward direction. Since the fluid is static, this upward force and downward force must be equal and opposite to each other. So this upward force is called the force of buoyancy. Now, this force of buoyancy is working because of the pressure differential that exists between top and bottom. Now, I imagine that the same mass of liquid is replaced by uh, some solid body having the same volume or same shape as that of the liquid mass. So once you take this as a solid, then now the weight of the solid which is working down, but the external force are same as that in this case. So external force, which is force of buoyancy, the net force because of the fluid pressure difference is working upward. But as in this case, the weight of the fluid and the net external force were equal. In this case, they may be equal, they may not be equal. So if they are equal, then the solid will remain afloat in the liquid. If the buoyancy is more, and say if it's a hollow body, weight of the body is less, then the body will be net body will experience net force in the upward direction, and it will accelerate upward. If the body is a heavy, say a very highly dense body, then the weight of the body will be more, and it will move in the downward direction. Remember, the buoyancy depends only on the volume and the density of the displaced fluid. Examples are floating balloon, we are familiar, floating fish, hydrometer. Hydrometer is an instrument used to measure the density of liquids. So that brings us to the floating fish problem. How do fishes go up, down in the tank, fish tank? I mean, most of you have seen it in the fish tank. They keep moving up or down. The answer is very straightforward. The fishes have some kind of air sac in their body. So although their flesh is heavier than water and typically they should get drowned, the air sac reduces the effective density. Also, they can pump more air in the air sac by that way they reduce their density, average density, and they go up. If they decrease the air in the sac in their body, the density increases and they go down. Now we move towards what is called the fluid dynamics. It has two ideas that we need to discuss. One is fluid equation of continuity, and other one is Bernoulli's principle. So if I have a fluid which is flowing from a larger cross-sectional area to a smaller cross-sectional area, then at any time the volume entering, which is AV dt, has to be equal to volume leaving, and mass entering can also be used, figured out by multiplying the volumes by by rho. Now if the fluid is incompressible, then amount of mass entering the tube has to be equal to amount of mass leaving the tube, and therefore I can equate the two. If the densities are equal, and I'll come to the idea what will happen if the densities are unequal. If the densities are equal, then you get rho a1 v1 dt is equal to rho a2 v2 dt. Rho will cancel, dt will cancel, and that will give you a1 v1 is equal to a2 v2, which is our simplest form of equation of continuity. So if it's an incompressible fluid, a1 v1 is equal to a2 v2. If it's a compressible fluid, then in that case your density will also vary as you go from here to here, and therefore it becomes rho 1 a1 v1 is equal to rho 2 a2 v2. It's a compressible fluid. Volume flow, a term which will often come in your study of fluid mechanics, which is defined as the volume of water or any fluid for that sake flowing per unit time. So dV by dt, this is volume. So amount of volume flowing per unit time is actually cross-sectional area into velocity at that instant, at that point. I continue here and I present an equation. This is how the equation of continuity look like if your fluid is compressible and if you use a bit of vector calculus. So what it says is that del dot rho u is the velocity, flow velocity, a vector field. It's a dot product, remember this is a vector del, and rho is the density. And if the density fluctuates, then the density fluctuation is d rho by dt. Remember this is a divergence, del dot uh, whatever rho u is a divergence of this term. So divergence of rho into u is basically equal to negative rate of fluctuation of density. So what it means is, suppose I take it on this side, then it becomes negative. So what it means is, if your fluid is diverging from the source, then the density will drop and the divergence will increase. So it's more like a Gauss theorem for electrostatics, where the divergence of electric field is equal to amount of charge in the uh, uh, is the rate of change of the charge present in the given volume. So you have done that Maxwell's law, more or less the similar concept. Now, if your density is constant, then this becomes 0. That brings del dot u to be equal to 0. And if you work out from here also, you can derive this equation. We also assume an irrotational fluid, and for an irrotational fluid which is needed for Bernoulli's principle, the del cross V is 0. So there is no rotational component. So velocity vector of the fluid motion, if you take its cross product with the del operator, it has to be 0. It has a strong need in Bernoulli's equation, because it says that the net work done on a fluid element by the pressure of the surrounding fluid equals to the change in the kinetic energy plus the change in the gravitational potential energy. But the way we write, we assume that the fluid is not rotating, because if the fluid is rotating as well, then there will be some rotational kinetic energy that you need to introduce. So most of the Bernoulli equation problem assumes that it is an irrotational incompressible fluid. Again, I take a small section of fluid in a pipe, and displacement is v dt. At this point it is v1 dt, and at this point it is v2 dt. And the volume flow, as we have seen, is area into cross-sectional area into displacement. So A1 ds1, A2 ds2, and at both ends the forces are going to be pressure into area. So here P1 A1 and here P2 A2. So the net work that will be done by the external forces are going to be the difference in these forces multiplied by displacement, force into displacement. Once you do that, you get, look at these forces are P1 A1, displacement is ds1, P2 A2 ds2. Now A1 ds1 is volume flow dV, A2 ds2 is volume flow dV. Remember, the volume flow has to be same if it is incompressible fluid. So P1 minus P2 into dV comes as common. So that is the net work done. Now this work gets used in many ways to increase the kinetic energy or to increase the potential energy. So I find the kinetic energy of the elements, and I calculate the change in the kinetic energy as the elements move from this end to this end. Then I calculate initial potential energy, final potential energy, and find the change in the potential energy. So I have my work done, I have my change in total mechanical energy. I can use the conservation of mechanical energy principle. Change in work done, the amount of work done is equal to change in mechanical energy for a fluid where there is no loss, there is no rotation, there is no compression, and I can straight away write the equation. This is the work done, this is change in kinetic energy, this is change in potential energy. Rearrange the terms, and I get a similar term on both sides. P1 rho g y1 plus half rho v1 square, P2 rho g y2 half rho v2 square. Remember, since 1 and 2 are chosen arbitrarily, this has to be true for all the points in the fluid, and therefore the sum of these three quantities are always constant. So So I can write P plus rho gy plus half rho v square is constant. A beautiful way to remember this equation is, this is pressure obviously. Rho gy is potential energy density. Imagine this as mass and potential energy is mgy. Now you divide it by volume. So mass upon volume becomes density. So this is potential energy per unit volume, potential energy density. Similarly, half mv square is kinetic energy but divided by volume. Mass upon volume will give you density once again. So half rho v square gives you the kinetic energy density. So what Bernoulli's energy says, that in fluid at any instant, at any time, at any position, the sum of the fluid pressure plus potential energy density plus kinetic energy density is always constant. And remember, here we are talking about a moving fluid. So this is what is called Bernoulli's equation. Applications are tremendous. Water pressure at your home, it could be more or less depending on what height it is coming. Speed of efflux. So if you have opening in a box, the speed is decided by Bernoulli's equation. Venturi meter, lift of an airplane. So here is the classic example. Almost at the same height, front end and the tail end, but the airflow is, here air travels a longer distance, so the speed relative to plane is less on the top, speed relative to plane is more at the bottom, and as a result a pressure differential comes in, and because of the pressure differential the plane takes a lift in the upward direction. Okay, do we have more time? I don't think so. It's 10:52, so I must stop. We can talk about viscosity and turbulence if you all need later in the next class. So, thank you. You all can join the Google Meet with the same link as it was used for the previous session.